So in the Farkas lemma, our objects are two: a matrix with general dimension. We don't really need to care whether this matrix is square or basically fat or skinny or anything. And then there is a vector. Okay, so Farkas lemma, you need to basically to apply it. It operates on a matrix, okay, and a vector. And it tells you that one and only one of those statements is true. So the first statement is that there exists a non-negative vector x. Okay, so of course x greater than or equal to 0, this is to be understood to be element-wise. Element-wise, okay, so a non-negative vector x such that ax is equal to b. So basically the first statement here tells you that you can write b as a non-negative combination of the columns of A. Okay, so you can find an x, not an arbitrary x, but x that is non-negative element-wise, such that ax is equal to b. Okay, so that's one alternative. So this thing is true, or if it's not true, then something else will be true, that there exists a vector now in Rm by 1, okay, so such that y transpose A is greater than or equal to 0, again element-wise, and y transpose B is less than 0. Okay, so one of these two statements must be true and the other must be false, and again these statements are related to some given matrix and some given vector. Okay, so let's prove that this is the case. First, let's refute the possibility that actually the two statements can be true at the same time. We will do it by way of contradiction. Suppose that basically these two statements are true. Okay, so if they are both true, then you can find the non-negative vector x such that ax is equal to b. But at the same time, you can also find vector y such that y transpose A is greater than or equal to 0 and y transpose B is less than 0. So you start with this one and multiply by y transpose from the left. Multiply by y transpose from the left. Okay, because you're assuming that both are true. Okay, then what? Then y transpose A is, okay, so y transpose A is a row vector. A row vector that is non-negative. That is non-negative, right? Because you have this. Okay, what about x? We are assuming that both statements are true. X is also non-negative column vector. Okay, and what happens when you multiply them? Well, when you have the inner product, then you should get something that is non-negative. But at the same time, the second statement tells you that y transpose B is strictly negative. Okay, and so you cannot have this equality. It cannot be true, right? Because one side is non-negative and the other side is strictly negative. Okay, and so basically, the two statements cannot be true at the same time. So our next step is basically to assume that the first statement is false, okay, and then to show that if this is the case, then the second statement must be true, okay. And so we'll assume that the first statement is false. By false, we mean that you can never find a non-negative vector such that ax is equal to b. And now you need to show that basically the second statement is true. How can we do that? Let's define set big S to be the set of vectors Z that, such that those vectors, so they are basically the vectors in the m-dimensional space that can be expressed as non-negative linear combinations of the columns of A. So we collect in this set all vector Z such that ax, you can find an x that is non-negative element-wise and ax is equal to z. Okay? And when we say that our first statement is false, we are basically saying, you know, the B vector of Farkas Lemma is not in S, because S includes every possible m-dimensional vector that can be written down as A multiplied by X, where X is a non-negative matrix. Okay. Now, set S is non-empty. So S is non-empty. How do we know that it is non-empty? There is at least one vector that is guaranteed to be in S, which is, what is the vector that is guaranteed to be in this set? The all zero vector, right? Because the all zero vector, you know, can be written as A multiplied by the all zero vector, right? So we want X, you know, the components of X need to be greater than or equal to 0, okay? So basically this set is non-empty, okay? You can always find, you know, an element, and, you know, the easiest element to think about is the all zero vector. Regardless of matrix, what matrix A is, if you multiply A by the all zero vector, you get the all zero vector. So the all zero vector is living there, so S is non-empty. Now, if S is also closed and convex, okay, so I mean, you see where I am going. I'm trying basically to make use of the separation theorem I mentioned in the previous lecture, okay? So let's basically go to the side and remind ourselves by this theorem that if S is, so if S is non-empty, okay, and closed and convex, okay, so non-empty, closed, and convex, then there exists a vector Y, or let's call it here another name. There exists alpha, such that alpha transpose Z is strictly greater than alpha transpose X for every Z in S, and given X that does not belong to the closure of S, which means that the distance, so this thing near here, that the distance between X and S is strictly positive, right? So this was the result, you know, the last result in the previous lecture, that basically have a set that is non-empty, closed, and convex. You can always find a vector such that the inner product of this vector with every vector in the set is strictly greater than the inner product of the vector with some you know, some vector or some point that is outside basically the set. Okay, it's not in the set, it's not in its closure. Specifically, the distance between that point and the set is strictly positive. Okay. So if S, you know, so S is non-empty, this is easy to check, and also it is easy to check that S is convex. What is it changing actually that S to show is that S is closed. But if, you know, so take this for granted for now, if S is closed and non-convex, then we have this vector Y, such that Y transpose Z is greater than Y transpose B for every Z that is not in S, because basically we are assuming that B is not in S, because we are assuming that actually the first statement here is not true. And our objective is to show that if the first statement is not true, it must be the case that the second statement is true. Okay. Now, since you know that this inequality is valid by the separation theorem, is valid for every vector in set S, let's strategically choose some vectors from S. So the all zero vector is in S, okay? So it must be the case that Y transpose multiplied by the all zero vector, which gives you 0, must be strictly greater than Y transpose B, right? So Y transpose B must be less than 0. Okay, again, this statement is true for every Z that is in S. One of those Z's is basically the all zero vector. So it must be the case that 0, which is the inner product of Y and the all zero vector, is strictly greater than Y transpose B, which means that Y transpose B is strictly negative. Okay, what else? There are also some vectors, you know, some vectors that are guaranteed to exist, you know, to exist in Z. Okay, so choose a big M that is basically positive, and big M times a column of A is in S. Right? So basically, this is the jth column of A, right? Because now if you take matrix A and you multiply it by a vector that is 0, 0 here, and then you have big M and then 0, okay? And where big M is positive, what is the result? What is the result? You will basically get the mth, so if this is in the jth position, so you get A column J, okay? And this is a non-negative vector, so this is non-negative. Okay, so so basically the multiplied by M, of course. So this is M times the A column J. Okay, so M AJ is in S. Okay, so again, since this inequality from the separation theorem is valid for every vector Z in S, then what we can do is basically use for Z M that is a positive scalar multiplied by a column of A. So Y transpose multiplied by MAJ must be greater than Y transpose B. Okay, M is positive. You can divide both sides of the inequality by M, and so Y transpose AJ, which is the jth column, must be strictly greater than 1 over M Y transpose B. Now, M should be positive, but you can make it arbitrarily large, right? For every positive M, this inequality will be true. So M can be a huge number, okay? And because of this, because this inequality is true for every M, you can show that, you can make an argument that actually this means that Y transpose AJ must be non-negative. And this is true for every jth column in matrix A. Okay? So, we basically, again, we took the first statement to be false, and we proved that if it is false, then B is not in the set S, which is the set of all vectors in the m-dimensional space that can be written as AX, where the components of X are non-negative. Okay, so B is outside this set. We used the separation theorem to show that there exists a Y such that Y transpose Z is strictly greater than Y transpose B, and then we chose basically vectors in set S to actually show these two results, that Y transpose B must be strictly negative, and Y transpose A is strictly positive, which just means that Y transpose multiplied by any column in A must basically give a non-negative result. Okay? But the proof is definitely not complete, because to be able to use the separation theorem, we need to show that set S is convex and closed. As I said, convexity is not a big deal. Take two vectors in S, okay, and because these two vectors are in S, then you can find a non-negative x1 and the non-negative x2 such that we have these two equations here. Okay, now let's examine lambda z1 plus 1 minus lambda z2 for lambda between 0 and 1. So simply what you can do is that multiply both sides here by lambda, multiply both sides here by 1 minus lambda, and add, and you get that this vector is A multiplied by this vector. By this vector is, so if you take a vector x1 that is that has non-negative components, x2 that has non-negative components, so if you take lambda x1 plus 1 minus lambda x2, it's guaranteed to be with non-negative components. Okay, so the point here is that if you start with two vectors in S, any convex combination of these two vectors is guaranteed to be in the set itself. Okay, so the set is convex. That's actually the definition of a convex set. The challenge is to show that it is closed. Okay, any questions? Okay, so everything I said on the previous slide is nonsense if set S is not closed, because basically the separation theorem requires that set S is a closed set. Okay, so how can we prove that the set is closed? So from your knowledge of analysis, you know that there are typically like two ways to show that the set is closed, right? So to show a set is closed, you know, so there is one way to show that the complement or its complement is open, right? Okay, sometimes this is the way to go. Sometimes the most convenient to prove that a set is closed is to show that its complement is an open set. And then, or this, the other way of proving is show that that all limit points of converging sequences in the set are in the set. Okay, so again, these are like two general methods for proving that the set is closed, and we will go for the second one. Okay, so we want to show that this set is closed. Okay, so let's try to establish a fact which will be very helpful in basically showing that the set is closed. Okay, so you take a vector. I mean, if Z is in the set S, it means that there is a non-negative vector X such that AX is equal to Z. Okay, but here is another claim. Any vector Z can be written as AJ big J alpha. So what is this? Any vector can be written as, you don't use all the columns of matrix A. You use just the subset of the columns of matrix A. Okay, so this is basically AJ is the column submatrix of A indexed by J, and J is a subset of the set from 1, 2, 3 up to N. Okay, so perhaps AJ is the first, third, and fourth columns of A. This is not a big deal, right? Because if Z is equal to AX, basically if vector X contains zeros, then you can basically eliminate the columns of A corresponding to those zeros, and write Z in terms of basically the remaining columns and a vector alpha that contains strictly positive elements. So this is not a big deal, but the big deal is this. A is equal to J alpha, where alpha is strictly positive. Again, this is not a big deal, but also alpha has minimum cardinality. And at the same time, the columns of AJ are linearly independent. So what does it mean that basically vector alpha has the minimum cardinality, or that basically the index set, the column index set has minimum cardinality? It means that you cannot basically express Z as a positive combination using a fewer number of columns. Okay, so we want basically so again, this is a claim. I mean, it's not clear. What is clear that, again, like if AX is equal to Z and there are zeros in X, again, you can basically get rid of the columns of A corresponding to the zeros. But now we are basically making a stronger claim that basically this index set has minimum cardinality, and also that AJ is full column rank, which means that the remaining columns are all linearly independent. So to show this, again, let's do it by way of contradiction. So suppose that you can write down this thing with again vector alpha that is strictly positive, and you take the minimum possible number of columns in A, but the columns of AJ are linearly dependent. Okay, so the trick here is to show that if the columns of AJ are linearly dependent, we can actually get rid of at least one more column. So we can express that as a positive combination of a fewer number of columns. Okay, again, let's do it. So suppose that the columns of AJ are actually linearly dependent. This is contrary to our claim that the minimum cardinality corresponds to basically linearly independent columns. Well, if the columns are linearly dependent, there exists a vector gamma such that AJ gamma is the all zero vector, and at the same time this vector gamma is non-zero, which means that gamma is guaranteed to have a component, at least one component that is non-zero, right? So if you have a matrix and its columns are linearly dependent, basically its null space is non-trivial. Okay, this is exactly what is being said. The null space is non-trivial, which means that you can find a non-zero vector gamma such that AJ gamma is equal to the all zero vector. Okay, so now AJ gamma is equal to 0, then so Z is equal to AJ alpha, right? Also, it is equal to AJ alpha minus tau gamma. Why is this true? Because we know that AJ gamma is equal to 0, because AJ gamma is equal to 0, and tau here is a constant, right? In other words, that if basically the columns of A are linearly dependent, then I can write this, or I can write this for any tau, right? Because AJ gamma is equal to the all zero vector. Okay. So what we will do is that we will strategically choose a value of tau such that this vector alpha minus tau gamma, okay, becomes a non-negative vector, remains a non-negative vector, okay, but with one or more zero components, which means that actually we can express Z as a positive linear combination of fewer columns of A. Okay, and the value of tau that achieves this is simply this value. Okay, so choose tau to be alpha of k over gamma of k, where k is defined to be the minimum of those. So what you do is the following. You know vector alpha, it's a vector of positive elements. Okay, you know vector gamma, and exclude the components of gamma that are equal to 0. But we are guaranteed to have basically some non-zero components in gamma. So over those non-zero components in vector gamma, search for the index for which this quantity is minimized. So the quantity is alpha v over the absolute value, or the magnitude of gamma of v. Okay, you can check. Okay, and I did basically this check for you here. You can check that if you choose this value for tau, then alpha plus tau gamma, so this vector, actually it's alpha minus tau gamma, so this should be a minus, alpha minus tau gamma, and tau is given by this quantity here, alpha minus tau gamma. Now it has at least one zero component, and the other components are basically positive, which tells you that you can express vector Z actually using fewer columns of A. So this establishes basically our result that if you have Z in this set S. So again, if Z is in S, you can write Z as A times X, and X has non-negative components. But what you can do is that you can write Z as a collection of the columns of A multiplied by a vector that is strictly positive. Okay, and those columns of A can be, basically you can find them, such that they are linearly independent. And the procedure explained here tells you that if you find a collection of columns of A to express Z, and those columns of A are linearly dependent, this procedure tells you what you should do so that you obtain a linearly independent collection of columns of A, such that Z is equal to a positive combination of those linearly independent columns. Okay. And you can show that basically this representation of Z is unique. Okay. So suppose that Z is equal to AJ alpha 1 and AJ alpha 2. Again, alpha 1 and alpha 2 are strictly positive, and AJ is full column rank. Then basically move this to the other side. Then AJ times alpha 1 minus alpha 2 is the all zero vector. But if the columns of AJ are linearly independent, okay, then to multiply a full column rank matrix with a vector and get the all zero vector, it must be the case that this vector is the all zero vector, which means that actually alpha 1 is equal to alpha 2. So the representation, this representation is unique. Okay, and actually we can write down, okay, so now Z is equal to AJ alpha, multiply both sides by AJ transpose AJ inverse AJ transpose. Okay, so when you do this, now this thing makes sense. Why? Because we are sure that the columns of AJ are linearly independent, so this matrix inverse exists. Okay, so if you do this, you get that inverse AJ transpose Z is equal to AJ transpose AJ inverse AJ transpose AJ alpha, and this gives you identity, so this is equal to alpha. Okay, so alpha is in fact given by this expression here, and it's unique alpha. Now for every Z there is a unique associated alpha. Again, if you know that a Z is in set S, you can take it a step further, and you are able to express Z as a matrix, not A, but a collection of the columns of A that are linearly independent, and a corresponding alpha vector that is strictly positive. Okay. Now, okay, so we need to show that S is a closed set. So again, as I said, that one way of showing that the set is closed is take an arbitrary sequence in this set that converges. Okay, so I will take Z1, Z2, Z3, and so on. So that's a converging sequence in A. Converging means that it goes to some limit. Well, if we can show that this limit is in the set S itself, we are done, right? Because if you choose an arbitrary converging sequence that goes to a limit, and regardless of the sequence and of the limit, the limit is guaranteed to be in the set S, that's exactly the definition of a set being closed. Okay, the set being closed means that any converging sequence in the set goes to a limit that is an element of the set itself. Okay, so we will take this sequence. Okay, now first order of business is you take each vector in this sequence, and you express it using what I have just explained. Okay, so you express it as a strictly positive vector with minimum cardinality, and the corresponding column of AG are linearly independent. Okay, and actually the index here, I mean, will depend on. So I think it's better actually in notation that this is to have this J as a function of V. So you have a sequence, right? And each vector in that sequence may be expressed in terms of a different collection of columns in matrix A. I mean, who says that all of them will be represented by the same columns? Okay. However, having said so, you can always in this converging sequence obtain a subsequence in which the columns of A used are exactly the same. Why is this? Because basically the index sets are finite. I mean, if you choose columns from matrix A, you can you are basically talking about the subsets of the set 1, 2 up to n. This set has a finite number of subsets, right? 2 to the power n. This can be an extremely large number, but it is still a finite number, which means that the possibilities for AJ are finite. Because we have an infinite sequence, it must be the case that there is at least one possibility for the index set that continues forever. Okay, so there is at least one index set, let's call it J bar, that occurs infinitely often in the sequence. Because if every index set occurs finitely often, then basically the sequence is finite, which is not the case. We are basically taking an infinite sequence. So there must be some J bar such that never disappears. You can always find some Z that expressed in terms of those specific columns from matrix A. Okay, so we have a subsequence chosen from this original sequence such that Z of Vk, okay, is equal to A of J bar alpha of Vk. And we know the rules of limits. So if the sequence converges to some limit, then any subsequence extracted from the sequence also goes to the same limit. Okay, so if the original sequence converges to Z tilde, then also the subsequence will converge to Z tilde. We are interested in the subsequence again because we want basically this matrix to be the same. Okay, so again, what is the motivation of making this argument is that if you start with a converging sequence, again, each element in the sequence, we have Z1, Z2, Z3, may be expressed in terms of different columns from matrix A. But we want basically to focus on, to zoom basically onto a subsequence of those vectors Z that are all expressible in terms of the exact same columns from matrix A. Okay. Now, Now, some results that I expect that you already know from some previous study. Suppose that you have a group of vectors converging, okay, as v goes to infinity. Now, if you multiply, then, okay, so if this is true, then you can show, and it's not difficult, it's just 2 lines, you can show that, for some matrix B converges to BQ. Okay, so if you have a sequence of vectors converging to a limit vector, then multiplying both sides by b, you get this statement will be true, and the proof is straightforward. And the reason is that basically this difference between BQV and BQ can be upper bounded using basically the properties here of the induced L2 norm of of vectors and matrices, that basically this L2 norm is upper bounded by the L2 norm of the matrix, which is some non-negative number, and the L2 norm of this difference between the vectors. And this thing can be made arbitrarily small because we have this limit statement. So basically the difference between BQV and BQ can be made arbitrarily small. Okay, so that's the first thing. What else we need? The second thing is again a statement that you take like in a first course on calculus or real analysis, that if you have a positive sequence that converges, then the limit point is or the limit is either positive or at worst the limit is 0. Okay, but it cannot be the case. You cannot have a strictly positive sequence that converges to a negative limit. So the limit must be non-negative. Okay, so these are exactly what we need to finish off this proof that S is a closed set. Okay, so here is the idea. Here is the idea. Okay, so we know that Z of Vk converges to Z tilde. Okay, then if we multiply by this this statement is true. Transpose Z tilde. Okay, so this must be true. So if this is given, this must be true. Okay. Now let's call this thing. Call this vector. Call this vector 8. Okay. Now what is this? What is this? What is this quantity? So if we go to the representation of Z. Okay, so we show that Z can be expressed as a strictly positive combination of a certain selection of linearly independent columns in matrix A, and this positive vector can be written as this matrix multiplied by Z. Okay, so basically this quantity here is alpha Vk, and basically those are vectors that are strictly positive. So those are vectors that are strictly positive and they converge to eta. Okay, so we have strictly positive vectors that converge to eta. So what is the conclusion regarding eta? Thus, so you have a vector. Every component in the vector is strictly positive. Exactly. No, not positive. Not necessarily positive. I mean, it can, non-negative. Okay, so the thing to say, exactly. So basically, I always think of 1 over n. So 1 over n is strictly positive for every natural number n, but it converges to 0, right? So what we can say, objectively speaking, that eta is greater than or equal to 0. Okay, so it must be the case that eta is greater than or equal to 0. Okay, so we have basically this alpha vk must converge to eta, and now because the alphas are strictly positive, then eta is greater than or equal to 0. Okay, so we have alpha vk, so converges to eta as k goes to infinity, and this is a non-negative components. Now, if this statement is true, then now we know that if you multiply from the left by a matrix, you are still true. Then Aj alpha vk converges to Aj multiplied by eta. Then Aj alpha vk is equal to Aj multiplied by eta. Okay, and what is this thing? Aj, then so this thing is exactly equal. This thing alpha vk is basically z vk. Okay, so z vk converges to Aj eta. So where are we? So again, let's basically summarize the argument. The argument, it's not as as difficult as it may seem. So here is the story. Okay, so again, you consider a converging sequence. Okay, from that sequence you extract a subsequence with the same matrix Aj. Okay, because you want just a matrix that does not change with the index. Okay, and from the rules of the limit, the subsequence will also go to this z tilde. Okay, so we have a subsequence that goes to z tilde. Now multiply by this matrix. So basically this sequence will converge to basically this vector here, which we call the eta. But this sequence is basically the alphas. And basically those are vectors with strictly positive components. So if they converge, and they do converge here, they converge to a vector with non-negative components. So eta is greater than or equal to 0. Now multiply by Aj. So now we can say that ZVK converges to Aj eta. Now, but we initially said that ZVK converges to what? To Z tilde. Z tilde, exactly. So, by the uniqueness of limit, these two things are the same. Okay, so these are the same. These are the same, right? And so Z tilde, okay, thus Z tilde is equal to Aj eta. Okay, so Z tilde is a non-negative combination of some columns in A. Then Z tilde belongs to set S. Because set S is basically this set that contains all vectors that can be expressed as as basically matrix A multiplied by a non-negative vector. Okay, and so if you start with a converging sequence in the set S, it goes to a limit, and now we have shown that regardless of this sequence that we start with, you end up with a limit, and this limit is guaranteed to be in the set itself. That's exactly the definition of a set being closed. So set S is closed. Okay, it is a closed set. Okay, so it's interesting proof, but the idea I took some time to explain it, because it is fundamental to prove the Farkas Lemma, and the Farkas Lemma we will use it actually to explain or prove very, very important results like strong duality in linear programming and KKT conditions, and we will use it again in Markov chains. So I thought that we should have the full proof of the Farkas Lemma, and this will include this proof that set S is closed. Okay. on Blackboard, I mean, if you don't like, you know, the way I explain the proof, I mean, you can read it from the book Numerical Optimization, which I think you know the book. I think it's the book that you are using, or at least it's one of the references in the Numerical Optimization course. Okay, so you will find the link basically to the chapter in which like the KKT conditions are proved, and I think in an appendix for that chapter you find also the proof that S is closed. Okay. Okay, so now of course like linear programming is a big topic, and again in the optimization course I am sure that you will spend some time learning about linear programs and how they are solved, you know, simplex method, you know, ellipsoid method, you know, these things. In this course, you know, I will just do two things. I will introduce what a linear program is, okay, and I will make introduce a concept called the dual program, and I will show something called strong duality. Okay, so it's purely theoretical, so I'm not really explaining how linear programs are solved, because I mean this is outside the scope of this course. You learn it in something like AMCS 211 and so on. Okay, so what is a linear program? A linear program is an optimization problem in which both the objective function and the constraints are linear functions. Okay, so both the objective function and the constraints are linear functions. Okay, so that's the linear program. So here, now, what is the standard form of a linear program? It varies a lot depending on the reference you are reading. In this course, we will stick to a particular sort of canonical linear program, and it's given as such. Okay, so you need to stick to this format. So our standard linear program will be like this: maximize C transpose X. Okay, so what is C transpose X? It's a linear function. So it is C1x1 plus C2x2 up to Cn(xn). Okay, so the C's are given constants and they live inside vector C, and the X's are our optimization variables. We have n of them. Okay, so we maximize basically C transpose X. However, we have constraints. So subject to AX is less than or equal to B, where B is a given vector. Okay, so you can basically explain this inequality row-wise. Okay, so basically this thing here means that if we focus on the jth row, then AJ1x1 plus AJ2x2 up to AJnxn is less than or equal to BG. Okay, so as you can see, every constraint, so typically we collect those linear functions, the constraints, and put them in this matrix form: AX is less than or equal to B, and then maximize C transpose X. Okay. Again, you need to stick to this. So if basically you are using a different like sort of standard linear program in another course, I mean, please don't use it. I mean, here we will stick to this format again, because like the whole argument is like so. By the way, everything I said here is actually general, and it does not represent, it does not depend on how we write down our linear program, but like for convenience, we need like sort of stick to standard form. Okay. So this is our standard linear program, and again it's called the linear program because it's an optimization problem in which the objective and the constraints are linear. Okay, so let's write it here. C maximize subject to AX less than or equal to B. Okay. How to solve this linear program in practice outside the scope, but so here we will just have some theoretical thinking about linear programs. So suppose that you are, so this is a maximization problem. Suppose that you are interested in an upper bound on the objective function. So you are interested in you're upper bounding the objective function. Okay, then you say, okay, so pick non-negative vector y, okay, and multiply basically this thing here. So you have y transpose ax. Now, because the components of y are non-negative, basically you have this inequality preserved. Okay, so the idea is that you know, multiplying by y transpose is like let me write it explicitly. It's like taking each constraint and multiplying both sides by a positive number and then adding. It's like you take yj and then aj1x1 up to ajn xn, and this will definitely be less than or equal to summation j yj bj. Okay, so you go to each linear function in our constraint set, and you multiply by a non-negative number, so basically the inequality is preserved, and you add them, and so like in a compact way we write that y transpose ax is less than or equal to y transpose b. Okay, then what if we choose this quantity? Okay, if we choose a transpose y to be equal to c, then y transpose A is equal to C transpose, and C transpose X, this now becomes C transpose X, is less than or equal to Y transpose B. C transpose X is something very special in our problem. It's the objective. Okay? So basically we have this inequality. So if you choose Y to be greater than or equal to 0, and it also needs to satisfy that A transpose Y is equal to C. So for every Y that satisfies these two things, the components of Y are non-negative, and A transpose Y is equal to C, the quantity Y transpose B, okay, so for every Y greater than or equal to 0 and A transpose Y equals C, Y transpose B, which is B transpose Y also, is an upper bound on our objective function, which is C transpose X, C1 X1 plus C2 X2, and so on. Okay, so we have an upper bound. Okay, and you know, if you upper bound something, you may be interested in the least upper bound, you know, because this is like the closest to the true quantity you are interested in. So the least upper bound will come by solving a certain optimization problem, which is this: minimize B transpose Y, right? Because B transpose Y is an upper bound for every Y, but Y actually is not, you know, it's not any arbitrary vector. It must be greater than or equal to 0, and it must satisfy this. If you look at this minimization of an upper bound on the objective of the original linear program, what is this optimization problem? Its objective is a linear function of Y. Okay, so here the objective is linear. The constraints are linear. So basically, this problem is also a linear program. Okay, and so now we have two names. So the original problem is the primal program, the primal linear program, and now this problem here is the dual program. Okay, so again, let's have it this. So that's very important. So I have a primal linear program, maximize over X, C transpose X, subject to AX less than or equal to B, and the dual linear program, minimize over Y, P transpose Y, subject to Y transpose greater than or equal to 0, and A transpose Y is equal to C. And again, the motivation for the dual program was an attempt to upper bound, to have a bound on what the primal objective C transpose X can reach. It's an upper bound on basically the in optimization. There are some problems in which you cannot actually solve and you are satisfied with just some upper bound or lower bound or something like this. Okay, so this is an attempt to upper bound our primal program, but it results in another linear program. Okay, so you start with a linear program, you play this game, and you get another linear program. It turns out that these two linear programs are very related to one another. Okay, so let's assume that actually both optimization problems are feasible and have a finite objective. Because an optimization problem may be infeasible. Infeasible means that there is no vector satisfying the constraints. You cannot find any vector satisfying all the constraints of the problem. So this will be called an infeasible optimization problem. So let's now suppose that both linear programs are feasible. Okay. Now by design, so this is by design, C transpose X is less than or equal to B transpose Y for every X, such that AX is less than or equal to B, and for every Y that is non-negative, and A transpose Y is equal to C. Now, suppose that you have the solution to the primal linear program, and the objective when it's maximized is B star, which is CT times some X star, and basically the optimal solution to the dual program B transpose Y star is equal to Q star. Then by design we have this inequality here, right? So basically this is true for every feasible X and for every feasible Y. Then basically if you solve both linear programs by one of the methods that you will learn in some other course, then you are guaranteed that the objective of the primal program is less than or equal to the objective of the dual program. P star is less than or equal to Q star, and so this result is called weak duality. Weak duality. Not very surprising. It's like sort of, it's like it's inherent in what we did, an attempt to upper bound, and so basically this is what we get. But here is the surprising result. Actually, P star is equal to Q star. So if your linear programs are feasible and they have finite objectives, B star is equal to Q star. If you obtain the optimal solution to the primal program and the dual program, they're the same. So this is called strong duality. So it turns out that linear programs basically have this property called strong duality. So each program is associated with a dual program, and you solve this one, you solve that one, and you get the exact same result. This has consequences. So you can basically design efficient algorithms based on this idea that B star is equal to Q star and so on. Again, these are things that are outside the scope of this course, and actually I'm really bad in basically how actually optimization problems are solved. So it's not me who can talk about basically how these can be used for developing numerical algorithms, but it is true. It is true that actually you can exploit this equality to design efficient algorithms. So there are basically a class of algorithms called dual methods, which basically solve these programs simultaneously in a very efficient way. My focus here is to show that actually this is true, because it's not clear. This is easy. This is by design, but why is this the case? Okay, so let's use the Farkas Lemma to show this. Any question? Okay, so here is the trick. Here is the trick. If we are able to show that there exists Y, so if there exists a feasible Y, which means Y has non-negative components and A transpose Y is equal to C, such that B star is greater than or equal to B transpose Y, we are done. Right? Because B star is less than or equal to B transpose Y for every feasible one. Okay, so to show that B star is equal to Q star, I mean, we need to show that, you can find the Y, a feasible Y, such that basically B star is greater than or equal to B transpose Y. Okay, so how can we show this? So let's show it by way of contradiction. So again, another proof by contradiction, which is we will assume that there is no Y satisfying this inequality, and this will lead to nonsense. And so it must be true that there exists a feasible Y for which B star is greater than or equal to B transpose Y. Okay, so proof by contradiction. And we will do the proof. So basically this, the idea here is we will go for a proof by contradiction using Farkas Lemma. But to be able to use the Farkas Lemma, you need basically two things. You need a matrix and you need a vector. And there is this game between the matrix and the vector, so there are two statements. One of them is true and the other is false. So the first order of business is to decide what is the matrix that can be used in the application of the Farkas Lemma and what is the vector. Okay, so here is the idea. If there is a feasible Y such that B star is greater than or equal to B transpose Y, then if a quantity B star is greater than or equal to this quantity, you can say that, so this is equivalent to B star is equal to B transpose Y plus some non-negative gamma. If B star is greater than or equal to B transpose Y, then B star is equal to B transpose Y plus some negative quantity, which I will call gamma. Right? And so, basically, if this is true, then we have, basically, we can combine the constraints on vector Y in this form, right? So we have Y greater than or equal to 0, A transpose Y is equal to C, and now we also have that B transpose Y plus gamma, which is non-negative, is equal to B star. So we can collect all these basically in this form. So basically I have a matrix. So this matrix here have A transpose 0 and B transpose 0. So and I will compose a vector. So this vector is basically vector Y of dimension n by 1, and then I will stick this gamma here. Okay. So if you read this equation, so A transpose Y plus 0 gamma is equal to C. So that's this guy. A transpose Y is equal to C, and B transpose Y plus gamma is equal to B star. That's basically this guy, and Y should be greater than or equal to 0, and gamma should be greater than or equal to 0. Okay, so for this to be true, you should be able to take, okay, so a matrix which is A transpose 0, so that's a column of zeros, B transpose 1 Y, and you have a non-negative vector, should give you this. Okay, so this is the vector of the Farkas Lemma, and this is basically the matrix of the Farkas Lemma. And what we will do is the following. We will assume that this is false. Okay, so we will assume that this is false. In other words, guess what? You cannot find a feasible Y such that B star, feasible Y means that Y is non-negative and A transpose Y is equal to C. We cannot find a feasible Y such that B transpose is greater than or equal to B transpose Y. Okay, again, if this is true, automatically we have weak duality, right? And if we have this thing true, then combining this will show that B star is equal to Q star, which is the objective of the dual program. So what we will do is basically say, no, this is not true. This cannot be the case. So here is the beauty of the Farkas Lemma. So the Farkas Lemma will tell you, okay, if you challenge this alternative, then there is another statement that must be true. Okay, so that's the essence of the Farkas Lemma. There are two statements, related to a matrix and a vector. It must be the case that one and only one of these two statements is true and the other is false. The two statements cannot be true at the same time. The two statements cannot be false at the same time. Okay, so let's suppose that this alternative is false. I mean, it can, it's not true. Then, by the Farkas Lemma, there exists a vector such that, so let me remind you of the Farkas Lemma. Okay. And let's basically use like different names for the variable. So you get phi and vector, let's say beta. So Farkas Lemma tells you there are two statements. Basically that phi x is equal to beta and x is non-negative. You can express beta as the matrix multiplied by a non-negative vector, or remember what was the second alternative? The second alternative is that there exists a y such that y transpose phi is non-negative and y transpose beta is less than 0. So that's the Farkas Lemma. Okay, so what we'll do here, that's now the matrix for the Farkas Lemma. That's the vector, and what we'll say, since you are claiming that this is false, then it must be the case that we can find the vector eta and epsilon such that the inner product of this vector and the vector of the Farkas Lemma, which is basically vector C in the linear program, to which we basically insert an additional component with the value of B star, which is the optimal objective value for the primal program. So it must be the case that the inner product of this vector and this vector is strictly negative. This is what the Farkas Lemma is saying. Moreover, the inner product of this vector and each column of the matrix of the Farkas Lemma should be non-negative. This must be true. Why is this must be true? Because we are claiming that this is false. If this is false, you must be able to obtain a vector such that the inner product of the vector with this vector is strictly negative, and the inner product of this vector with any column in the matrix is strictly or is non-negative. Okay. So just write down the inner products in a convenient way. So this inner product will be that C transpose eta plus epsilon. So epsilon is the last component in this vector that must exist if the other alternative is false. Then C transpose eta plus epsilon B star is strictly negative. And here it must be the case that eta transpose A transpose plus epsilon B transpose must be strictly positive, and also that epsilon is strictly positive. Okay, and this one you can take the transpose of both sides. So basically, by Farkas Lemma, those must be true. If this is false, then those must be true. Okay, let's now show that this does not make any sense. So we will try to derive a contradiction. And we have this last component in this vector. It's non-negative. Okay, it is non-negative, and you see that it's non-negative because the inner product of this vector with the last column here will give you epsilon, and so epsilon must be non-negative. So it is non-negative, so we'll basically deal with the two cases. So what if epsilon is strictly positive, and what if it is equal to 0? Now, if epsilon is strictly positive, you can divide by it, right? So if epsilon is strictly positive, then you can write down something like this, and you can write down something like this. No worries, because epsilon is a strictly positive number, okay? But this is problematic. Why? This is problematic because now B star, the optimal objective, is less than C transpose multiplied by this vector eta, okay? So those are basically the first component. So epsilon is the last component in this vector, and vector eta is here, divided by epsilon. We can do this because epsilon is strictly positive. So C transpose multiplied by this vector is greater than B star, and A multiplied by -1 over epsilon eta is less than or equal to B. Okay, so those guys, how can we obtain them from here? Basically, this one tells you that B star is, move this to the other side with a negative sign, and now imagine that we have a vector that is basically -1 over epsilon multiplied by eta, and it's the same story here. Basically what we have is A multiplied by the same vector, and now it's less than or equal to B. What does this mean? What does this mean? This vector is primal feasible. Why? Because what was the primal problem? Remember, what was the primal problem? The primal linear program was to maximize C transpose X subject to AX is less than or equal to B. So anything that is feasible should satisfy this inequality here, and this satisfies the inequality. Okay, so this is a feasible vector from the point of view of the primal linear program. But C transpose multiplied by this vector gives you a value that is strictly greater than B star. What is C transpose by the vector? It's the objective function. So that's a contradiction, because B star by definition is the optimal value for the primal linear program. It's the maximum. So now we are saying that you can come up with a vector that is feasible and that can allow you to obtain an objective that is higher than B star, but this is nonsense because B star is the maximum objective. So that does not make sense. Okay, well, well, perhaps epsilon is 0. Perhaps epsilon is, so this will cast doubt on epsilon being positive, but what if epsilon is equal to 0? If epsilon is equal to 0, okay, again, let's go back to here, okay, to basically our inequalities. Sorry, not those. Epsilon equals 0 means that C transpose eta is strictly negative, and that A eta is greater than or equal to 0. Okay, so let's investigate this. So we have basically these two guys. Now consider the vector x star minus eta. What is x star? It's the solution to the primal program. So again, we are assuming that our primal program, somehow we were able to solve it. X star is a vector x that basically maximizes the objective, and the objective function that its maximum value is b star. Now consider x star minus eta. Let's examine ax star minus eta. Ax star minus eta is ax star minus a eta. Now, a eta is greater than or equal to 0, element-wise. So this means that minus a eta is less than or equal to 0, element-wise. Element-wise, right? And so basically, this quantity, and we know that ax star is less than or equal to b because x star is a solution to the primal program, so it satisfies its constraint. So ax star is less than or equal to b. And minus a eta is less than or equal to the all zero vector. So a multiplied by x star minus eta is less than or equal to b. So what is the conclusion? So x star minus eta is primal feasible. Okay. What about C transpose X star minus eta? C transpose X star is B star minus C transpose eta. But C transpose eta is, so this thing here is strictly negative. Strictly negative. And so B star minus C transpose eta is strictly greater than B star. So this vector here, x star minus eta, will be a vector that is feasible for our primal linear program. It satisfies the constraint that a multiplied by the vector is less than or equal to b, and at the same time, this vector, when you take its inner product with c, it gives you a value that is strictly greater than b star. But how can be the case if B star is the maximum objective for the primal program? Okay? So actually those contradictions mean that this alternative, that there exists a vector such that this and this, so this vector eta epsilon, actually if we assume its existence with these properties, then we get contradictions. So actually this must be false. This alternative must be false. And the Farkas Lemma is a theorem of alternatives. If this is false, then this must be true. And if this must be true, then there exists a vector y that is feasible in the sense that y is greater than or equal to 0 element-wise, and A transpose y is equal to C, okay, and at the same time B star is greater than or equal to C transpose y, to B transpose y, okay, this one. But we know from weak duality that this is always the case, so in fact B star is equal to Q star, which is the optimal solution to the dual program. So we have something now called the strong duality. So you try to upper bound the linear program. Okay, so let's basically summarize. Summary. Okay. Primal linear program. Maximize C transpose X subject to AX less than or equal to B. Okay. Then upper bound the objective. How do we upper bound the objective? Well, big Y that is non-negative, Y transpose AX is less than or equal to Y transpose B, which is the same as B transpose Y. Okay, and if A transpose Y is equal to C, then basically we have C transpose X is less than or equal to B transpose Y for every Y greater than or equal to 0, and A transpose Y is equal to C. Okay, so that's an upper bound on the objective. Then basically try to obtain the minimum, the smallest upper bound, the least upper bound. Okay, and so what we will do is that we will minimize B transpose Y subject to Y greater than or equal to 0, and A transpose Y is equal to C. And you look at this thing, oh, it's another linear program. It is another linear program. And so it will have this funny name, dual linear program. Okay, so this is the primary linear program, and then when we play this game, you have a dual linear program. Okay, and now you are sure by construction, so again, by construction, okay, let's give the assumption now. Assume both programs are feasible and have finite objectives. Of course, you may say, well, I mean, what if they are not? Well, you'll see a problem regarding this in the homework. Okay, so in the next homework, you will basically investigate what if the primal program is infeasible? What if it is unbounded above? What if the dual program is infeasible or is unbounded below? Okay, so you will basically do this in the homework. For now, I will assume that both programs are feasible and have finite objectives. That for every feasible X in the primal linear program, for every feasible Y in the dual linear program, what do we have? C transpose X is less than or equal to C transpose Y. Okay, so if B star is the maximum C transpose X and Q star is the minimum of C transpose Y, we have B star less than or equal to Q star. So that's weak duality by the Farkas Lemma. We actually have B star is equal to Q star. Okay. One of the things that you should know, I mean, you know, basically in our field, I mean, it's basically you must basically know this strong duality and linear programs. It's something that's so fundamental to know and understand. Okay. We will come, we'll come back. So basically, the difference actually between B star and Q star is given a name. So I mean, for future purposes, okay, Q star. Okay, let me write this with a different color. Keep this in mind. Q star minus B star is called the duality gap. Duality gap. It is 0 for linear programs that are feasible and have finite objectives. So this zero gap business is very important in optimization. Okay, so it turns out, that if so suppose that you don't have linear functions, you have general functions, non-linear functions, but basically if your optimization problem, it has zero duality gap. But of course, I mean, you may ask, how do we define the dual programs for a general program that is not linear? We will talk a bit about this later, but the idea is that if the duality gap is 0, you can always solve the optimization problem efficiently. So basically, why do people love convex programs? If you are solving an optimization problem and you discover that it is convex, you typically celebrate because the overwhelming majority of convex programs, they have zero duality gap. Okay, and so they can be solved efficiently. And there are non-convex programs that also have zero duality gap. But it turns out again that zero duality gap is good. Again, it allows you to solve basically your programs efficiently. Okay. Since we are in the land of optimization, we must talk about gradient descent. Okay, so any question? Okay, so since we have like a couple of minutes to go, I definitely will postpone this to the next time. So I will just start the topic, and our functions here will be C1 functions. Okay, C1 functions. So basically, those are functions that have partial derivatives that are continuous. Okay, so C1 function. So this will be our heroes. Okay, so in preparation for next time, okay, so our functions here have partial derivatives. So they are, you can differentiate them partially, but moreover, the partial derivatives themselves are continuous. I have partial derivatives that are continuous. Okay. And of course, the gradient vector is the vector of the partial derivatives. Okay, so the gradient vector, this one here, is basically the vector, in which like you differentiate with respect to x1, differentiate with respect to x2, up to x. Okay. So we want to talk about, basically what happened, a very important property for those functions related to its gradient vector. Okay, and we will like get an idea why basically this, you hear it like in machine learning. Machine learning is mainly problems in machine learning are actually mostly optimization problems that are solved using gradient descent. Specifically, they are solved using stochastic gradient descent. Okay, but the main idea is gradient descent, and so like in this course we will try to understand what is gradient descent, and it doesn't, is it guaranteed, like if you apply it, is it guaranteed to converge, stuff like this, because it's basically an iterative optimization technique. Okay, so again, once you have some iterations, then you wonder, will you converge to something? And if you converge to something, do you converge like to the thing that you are interested in, or something else, and so on.